Now in this video we are going to transform our single line diagram into a ETAP program in order to find the voltage drop in our system and the short circuit level. Okay, so the first thing you should know is that the voltage drop in our system, which we designed before, should not exceed 5% as a voltage drop. Okay, so the first thing we will go to ETAP. I'm using here ETAP 12. All of them are nearly the same except that the newer version, the higher and more effective version than before. Okay, so the first thing we will click on File and then New Project. We will name this one as voltage drop and short circuit. That's short circuit. Okay, then you will find here the unit system. In my own country I use the metric. If you are in another country which use English, you can select English. Okay, then we will click on OK. Now you will find here the username and full name and the description and the access level permissions. Okay, I will just take all of them because I am the only one here. Then we will click on OK. Okay, now we will maximize this window in order to put our elements. So the first thing you should know is that we will click on project. Okay, and then you will find here information. If we are having a specific project in a company, then we can put these details when we export our final document. So we can put the project title, the location, the contract, the engineer, remarks and comments. Okay, this is the first thing. Second thing is that we can click on project and then we can click on standards. Okay, so you'll see here that according again to your own country, you are using a 50 hertz or 60 or 100 frequency or a 250 hertz or a 400 and so on. So in my own country I use the 50 hertz system. Again, the unit system English or metric, I use metric. The standard in your own country, you are using the IEC or the ANSI system. Okay, I am using the IEC. So you'll see here that here we have the different elements which you are going to design the single line diagram. You will find here we have AC components and here the measurement parts such as the potential transformer, current transformer and so on. Here we have the DC component. So this all of these symbols are based on the IEC standard. If I change it to your ANSI, okay, and then click on OK, you will see that all of this symbol it changed during using the standard, which is the ANSI code. Okay, but since I am using the IEC, I will change it back to IEC. Okay, then OK, you will see that all the symbols are back here. So the first thing we will see is the single line diagram. You will find here we have a transformer and this transformer taking its power from a grid. Okay, so the first thing we will draw is the grid. So this one is called the power grid. You will click on it and just like this, you will find here you can put it anywhere. So I'll just click here. Now I am having my own power grid. Now we will double click on this grid. You will find here its name or the name, the connection 3-phase or a single phase. Of course it is 3-phase. And you will find here more information which you can find from the power grid in your own country. Okay, so you see the transformer is getting its power from power grid. You find this information from the government about or the electrical distribution company about the power grid, and then you put this information. For example, here you will find the rated kilovolt. In my own design here we used an 11 over 0.4 kilovolt. The 11 is the voltage which is the medium voltage from our grid. Okay, so I will put here the rated voltage as 11. Okay, now it is balanced or unbalanced. I will assume it is balanced because I don't have the information of the unbalanced. This information are taken from the, of course, the distribution company again, or from the power grid. Now you will see here the short circuit. Okay, you will find here a megavolt ampere short circuit. Okay, for this, of course, again from the power grid on my own country, for the 11 kilovolt, the megavolt ampere short circuit is 500, and the X over R ratio is 10. Okay, I'm talking about my own country in case of 11 kilovolt level, and my own country, which is Egypt. Okay, according to your own power grid, and this information you can obtain it from the government or the electrical distribution company. Okay, these values you don't preserve them in your own mind, you just get them from the distribution company. Okay, then we will click on OK. Now we have a source for our power, which is the power grid, which has a 500 megavolt ampere short circuit and operating at 11 kilovolt. This is the first step. Second step, you will see here we have a transformer. Okay, this transformer is 11 over 0.4 delta star grounded, and you'll find 11 over 0.4 kilovolt. Okay, so let's and 1 megavolt ampere. So let's get the transformer. You will see here the symbol of the transformer is here, two winding transformer, and put it like here, and just connect it from here to the grid. Okay, and of course all of these are one node, and this is called as a connection between them with a bus. Okay, so in order to make it show or showing the bus, we will right click on this or the bus, and then you will see here tick on the node. We will remove it. You will see here that we have a bus bar here now appearing, and you'll see here also the voltage beside it, 11 kilovolt. Okay, now let's go to the transformer. We have here a transformer, a two winding transformer. This transformer has of course, if you have a specific name for this transformer, you put it here, the standard ANSI or IEC, and you will see here the different types of the transformer, shell or core, 3 lamp or 4 lamp, if you have this information. Okay, now the important thing is the rating. The rating of the transformer, you will see here the voltage rating. The primary is 11 kilovolt. It took this value from the power grid, since the primary is connected to this grid. So the program automatically puts the 11 kilovolt in the primary of the transformer. The secondary is 0.4 kilovolt. Okay, now the power rating for the transformer is 1 megavolt ampere. You can change also from megavolt ampere to another value, which is kilovolt ampere, as you would like. Okay, now you will see here that we have the impedance for the transformer. Okay, you will see the typical Z and X over R, or typical X over R. The program or ETAP has a database for different types of transformers. Okay, you will see here that it is 1 megavolt ampere IEC liquid transformer, which means oil transformer, at 65 Celsius degree. Okay, you can change all of this from here. Okay, you can see here the shell or any of it, or you can also play in this settings. You will find here, for example, the type liquid fill, or it is a dry transformer. We'll find here the temperature rise, the classes, okay, the subtype. All of this information you can find according to the transformer in which you will buy for your own distribution or industrial area. Okay, so let's get back to the impedance. So we will say that we don't have the values, so I will take typical Z and X over R. So our program will automatically put values from its database or library about Z and X over R. Okay, now we will find here the tabbing. Okay, normally we don't use the tabbing except after when the voltage decreases or the voltage increases in our area. Okay, so we normally put it 0 here. Okay, then we will click on OK. So now let's make sure that our transformer is delta star connected. How we can do this? Okay, you will see here a menu, display options, and you will see here for each type of elements you put in this, you can choose whether you have the ID, rating, kilovolt, ampere, delta, star connection, or Z. Okay, so for the power grid, I would like to see it's kilovolt. The motors, of course, kilovolt, and the bus kilovolt. Okay, the node, we can say kilovolt 2. Now let's go to the transformer. Okay, I would like to see its connection, delta Y, tapping. Okay, and the kilovolt. Okay, and for the cables, we can forget about them, and then we can click on OK. You will see here that all of the values we would like to find, you will see it is now beside our element. For example, the transformer delta Y N1. Okay, so it is connected delta Y connection. Let's get back to the grounding, and you'll see here that the primary is delta connection and the secondary is Y and solid grounded. Okay, you can change from delta to star. Okay, now we have our transformer. The next step is that we have here cable. Okay, here we have a cable, 4 cables, 4 multiplied by 500, copper PVC, and 4 multiplied by 500. Okay, so we have here, forget about the earth in this voltage drop calculations. Okay, so what we concerned about is these values. Okay, so we have here the 4, the 3 phase and the neutral having a 500 millimeter square, and we have 4 of these values. Okay, so for each phase we have 4 for the primary, or 4 for the R, 4 for the S, 4 cables for the T, and 4 cables for the neutral. Now let's find these values, okay, or put these values into our program. So the first step, we will go to cable, okay, and click like this and connect it to the transformer, and you'll see here a bus. We can right click and transform it to node, and then this cable, double click on this cable. Okay, and you'll see here different types, number of conductors per phase. Okay, so we said here that we have 4 conductors for each phase. Okay, this 4 means R, S, T, and the neutral. 4 means that we have 4 of R and S, T, and the neutral. Okay, R, S, T, and the neutral. We have 4 of them. So the number of conductors per phase is 4. Okay, for each phase we have 4 cables or 4 wires. Now for the length, we'll assume a 30 meter. That's just an example. In the actual place or the actual industrial plant, you will find and measure this actual distance. Okay, now you will find here the library. This library will give you a different types of cable. You will find here different types and different numbers. Of course, according to your own design, you can select which of them. Okay, so for our design, we are using a polyvinyl chloride, which is PVC, and at the same time, we are using greater than, of course, 0.4 kilovolt. Okay, we'll find here 0.5, 0.7, and the cross-sectional area is 500, right? Let's see, cross-sectional area is 500. Okay, so you will find here that the one which is selected automatically, where is it? This one having a cross-sectional area up to 35. Okay, so it's not meant for us. Okay, we need 500. So let's see the 0.7 here. This 0.7 has until 500 and 630. Okay, so that's pretty good. Okay, so we'll choose this one, 500. We have here copper 0.7 kilovolt, which is okay since our voltage is 0.4 and this cable can withstand up to 0.7. Okay, so and the polyvinyl as we required or as it required. Then we will click on OK. So we have a cable of 500 copper and 0.7 kilovolt and at a 50 hertz, which we are operating on. Now let's go to the impedance. For the impedance, you will see here that we have, if you have the values, you put them, or if you don't have, then the program automatically put them from the library. Okay, then we will click on OK. Okay, so we put the values for our cable. Now let's go to another thing. We have here, after putting this one, we have here a bus bar. Okay, so let's draw this bus bar. Bus, then like this, and then we click on it and drag. Click and drag. Okay, now we will put like this to connect between them. Okay, so now let's see another thing. We have the first load here is 50 kilovolt ampere, 150, 500, and so on. So as you know that this one is a residential area. Okay, so we have dynamic loads and we have static loads. Dynamic loads means we have motors, and we have static loads like lamps and things which does not have or absorb starting current. Okay, so our loads are not pure resistive or pure inductive here or here or here or even here. Okay, the factory lighting and power sockets, the administration building, residential building 1 and 2, all of them does not have pure resistive or pure inductive. Okay, so the load which you are going to put is called lumped load. Okay, you will see here lumped load. Okay, this lumped load means that our load is mixed between resistive and inductive. Okay, so we'll double click on it and you will find here some information. We'll go to nameplate. The megavolt ampere here we have 50 kilovolt ampere, so we can change this to kilovolt. So we'll click on 50 kilovolt ampere. Now we'll find here another thing, the power factor. We assumed in our project 80%. Okay, and you will find here load type. You will find here constant kilovolt ampere and constant Z. Constant kilovolt ampere means we are talking about the dynamic loads. This one means the static loads. Okay, so most of our loads here in this 4 things or the 4 different loads are called, of course 80% of them are static loads. We don't have much motors here, so we'll click on here and drag it to 20%. So that means that we have 20% kilovolt ampere or dynamic loads and 80% constant loads. Okay, then we'll click on OK. So now we draw our first load. Second thing, we will draw our cable. Okay, so our cable here is 4 multiplied 35. So cable like this, connect between them and between our bus bar. Here right click, remove the node. Okay, double click on the cable. We said that we have a 35, right? Okay, so number of conductors is 1, since we have here 1 for each phase and the neutral. Now let's see the library. Okay, we have this type polyvinyl again 0.5 kilovolt. Okay, and we need 35. Then okay, so we have here 4 and 35 millimeter square. The length we will assume 40 meter. Okay, we assume 40. Okay, then okay, so draw. Now we draw our cable and our first load. Now we can simply select all of this and then right click, okay, and copy, okay, and then right click and paste, okay, like this, and or control V, like this, paste. We have 4 loads and another one paste. Then we connect like this, and move it like this, and okay, okay. So now let's see each of our loads. We have here 150 and 500. Okay, so this 150, 150, okay, and this one is 500, nameplate 500, okay. This one, okay, this one is 25, which is the third one. Let's see. Okay, 25, okay, and the last load is 297. But remember something here, 297, okay, but here our last load is the industrial motors or induction motors. Therefore all of these loads are dynamic loads, so we'll change the load type to 100% to dynamic loads, okay, and 0 static loads, because all of this 297 kilovolt ampere is made of motors or induction motors only. So we'll click on OK, like this. Okay, now we will change the cables. Let's see this one. This one is 240 millimeter square, so we'll just go to library, 240. Okay, we can find this in the 0.7, 240, okay. Then, and the length is 40, let's make it 30, okay. Now this one is 4 multiplied by 300 and 3 cables, so we have 3, and we said that's 300, okay. So library again, then we go to 0.7 and 300, okay. Now let's go to this cable. It is I remember 10, okay, 4 multiplied by 10, so 10, okay, we can just edit from here, 10, then okay. Now the last one here, library 0.7. Now let's see, it is 3 multiplied by 240 and 2, okay, 240 and 2, okay, so we have here 2, then okay. Now we draw our single line diagram in ETAP. Now we would like to find the values for our voltage drop and short circuit analysis. So the first thing you'll find here is that this point or this pencil means that we are editing our single line diagram. When we are doing the load flow analysis or the load flow, of course, to see the direction of the active and reactive power, and at the same time we see the voltage drop. We will click on this. Now we have the load voltage or the load flow analysis. Now we will click on this run load flow, and then okay. You will find here different values. Let's move it, okay, like this. Okay, so we'll find here this values of P and Q, and you can find this from this screen display options. You'll find here that AC for the different things like transformer, we would like to show the kilovolt. Okay, the power grid kilovolt, the motor, okay, and the cables. No, we need the bus bars, kilovolt. Okay, now the results here, you will find that the bus voltage, each of this percentage represents the bus voltage, and I would like to see as actual values, so I will click on volt. Okay, you can also choose to see the magnitude or the angle or both of them. Okay, now we will find here the power flow, these values. Okay, you will find here P and Q. You'll find here P plus JQ, the active and reactive power. You can change it as you would like. You can choose ampere or kilowatt only, or the Q only, and so on. Okay, now we can click on OK. Now we will find that here the values it changed for the load flow. We'll find here we have the input here 11 kilovolt on the bus bar, and also through the transformer. Now for this bus bar, you will see that we have a voltage of 338.5 volt, which means that the most of the voltage drop is on the transformer from 400 to 383.5, which means nearly 16.5 volt voltage drop on this transformer. The cable has only voltage drop of a 3. You will see the difference between them. And finally, to the loads, we have 377, 376, 377, and so on. So we have, you will see that here, due to the large impedance of the transformer, you will see that all of these values dropped less than 380 volt. Okay, so again, the 5% voltage drop, in order so that from the output transformer to the load, we need at the load 380 volt. Okay, so we'll find here that the voltage drop is greater than 5%. So what we can do. Okay, we have two choices. The first thing is that we edit this transformer. Okay, double click on it, and then change the tapping of the transformer. Okay, you know that when we are dealing with a transformer, high voltage side, which is 11 kilovolt, and the secondary 0.4, we will change the tapping of the primary. Why? Because at the high voltage the current is lower, which means we have lower sparking. But if we change the tapping from the secondary or the low voltage, then the current will be high and the spark will be high. Okay, so we change the tapping of the transformer from the primary side. So we'll change the tapping by negative 2.5. What does it mean? It means that we change the number of turns, we decrease the number of turns by negative 2.5. This will lead the secondary of the transformer to increase. So we'll click on OK. Then we'll click on Run Load Flow Analysis. You will find here that the voltage increased. You will find here 187, 186, 87, 88, 87, and so on. So the voltage here increased. Okay, so that is the first method. Second method we can do is that, let's delete this. We know that the induction motors, or for the industrial plant, the power factor must be at least 0.9. Okay, if it is less than 0.9, then you will have a penalty due to having a low power factor. Since our power factor here is 0.8, we can do something. Instead of, you know that this transformer supplies a current, this current carries the P and the Q, the active and reactive power. If we add here a capacitor to supply the reactive power, then the current absorbed by the transformer decreases, therefore the voltage drop on the transformer will decrease. What I mean, let's get back to the editing. Add a capacitor. Okay, like this. And we'll put the value of the capacitor, for example 200 volt ampere in the information rating. Okay, 200 kilovar. Okay, now if we run the power flow, you will see that the voltage here increased, okay, to greater than 380. Again, just by adding this capacitor, we improved the power factor by adding this capacitor and providing the Q and decreasing the Q provided from the transformer. Therefore, we were able to decrease the voltage drop on the transformer and increased all of this voltage instead of and the tapping of the transformer is the same, 0. Okay, so these are the two solutions. If you don't need to change the transformer, we would like to make it 0 tapping, then we will put here a capacitor in order to improve the power factor and decreasing the voltage drop again. Okay, so that is the second thing. Okay, now let's delete this. Now we learned until now how to design or identify the voltage drop. Now let's go to the short circuit analysis. This one. In the short circuit analysis, you will find here a different setting you can do. Okay, you will find here a 3-phase fault. You will find here a single line to ground fault. You will find here a line to ground, line to ground, 3-phase faults, and so on. And you will find here run transient short circuit, run arc flash according to IEC, and so on. Okay, and of course here we have the display options. The display you can display as a peak or root mean square. The important for us is the root mean square value of the current, not the peak value. Okay, so now the worst type of short circuit is the 3-phase short circuit. So we design our short circuit or the capability of our cables, motors, or everything, bus bars, on the 3-phase short circuit because it is the worst type of short circuit. Okay, so where are we going to do the faults? Okay, we need a fault on this bus bar. Right click and then click on fault. We need a fault here, this one, and let's see what will happen. Okay, now if we run the 3-phase short circuit test, okay, you will find here the short circuit current. In case of a short circuit on the bus bar, you will find that the current is 28.8 kilo ampere. So our bus bar must withstand a short circuit value greater than this value. Okay, of course for a short time, not the short circuit rating of the bus bar must be greater than 28.8 kilo ampere. You will find that this value is 24.897 from the source or the grid, 2.56 kilo ampere from the induction motors, as the motors transform into generators during transiently, of course, during the short circuit. Here 0.045, 0.899, 0.271, 0.09 kilo ampere. Okay, for the short circuit, for example, here you will find on this bus bar, you will find 17 ampere coming from all of the other components and 2.7 from the motor itself, 20 kilo ampere. So this one must withstand 20 kilo ampere. Okay, this one 2.7 kilo ampere. This one 21.5 kilo ampere, 15.8, 7.4 kilo ampere. So we must design our elements according to the short circuit or the worst case. Okay, we can design all of this as a 25 kilo ampere and this one as a 30 kilo ampere. Okay, So finally we will click on report manager, and then you will find here the path. We will click like this. If I would like our results, the summary and everything about what we did now in the short circuit analysis, and we can put it as a PDF, Word, or any form, and then we will click on OK. Now for the load flow analysis, we can run it again. Then we can click on report manager and do the same, okay, PDF or anything. Okay, by doing this here, we can find the different things we have done in this program. Okay, so now in this video we learned about voltage drop and how to calculate the short circuit level using ETAP.